In the previous part, we discussed the frequency response of a system. And basically what you have is for different input of a sinusoidal function of sinusoidal signal, the steady state output of the system will be determined by the frequency of the input signal, but also by the transfer function. So you need to work out the magnitude and the phase angle from the transfer function. Then you can see how the output response will behave in steady state for that particular sinusoidal input. If you change the frequency of the input, then the magnitude and the phase angle from the transfer function will also be different and needs to be recalculated. If we do enough calculations for a good connection of AC gains, that's magnitude and phase angle, at different frequencies, or we can find some rules for the frequency responses, we can actually plot, we can draw the frequency response diagrams, and these frequency diagrams are a very useful tool for the design of closed-loop control systems. So in this part, I'm going to discuss one of the design techniques. It's called frequency domain design for closed-loop system. It is one of these sort of classical design methods. Unlike the locus design, where you could only tune one single gain, the frequency domain design allows us to design dynamic controllers, i.e. the controller with transfer functions. Okay? You could also design things like PID control for closed-loop systems. And the aim is to use the frequency response of the open-loop plant, that's the object for your control, to design the closed loop and predict how the closed loop system would behave or would perform. Okay, that's really the aim. So we don't have to assume a closed loop transfer function, or we don't have to assume we know the control gains or the controller and derive the closed loop system, or to derive the closed loop transfer function. Otherwise, it would be pointless. So the aim is to design the controller from the open loop transfer function of the plant and then predict what is going to happen or what's likely going to happen to the closed loop system. That's really the aim. But we're going to do that based on the frequency response diagrams. Just a quick reminder. These are two diagrams that are introduced. On the left-hand side, we have the bold plot for a transfer function, and where you have the magnitude against frequency and the phase angle against frequency. On the right-hand side, we can use something called a Nyquist diagram or polar diagram, where you actually connect all the AC gains at different frequencies together to form the plot. Okay, either plot can be used for control design. It's most of the time it's actually down to personal preferences. Some control engineers like to use polar plots. Some people like both plots, and there are other plots as well, like Nichols diagram, things like that. So everybody will have their own personal favorites. I like both diagram better because it tells me everything about the system or the open loop system in a very straightforward way. So I can see them better, I can interpret them better. Okay, so therefore I would recommend the way That's the method we should focus on. But both can be used, or either can be used. It really doesn't make a difference. Okay. So to start with the control design, we need to get familiar with a couple of stability criteria, because one of the first aims when you design a closed-loop control system is to maintain stability. So we need to know how can we determine if a closed-loop system is stable from open-loop transfer function. Okay, that's really the basis of control design. If you can't make that judgment, then the life would be much harder, because then you would have to, for every possible controller, you would have to derive the closed-loop transfer function, check the poles, and stuff like that. It's not always very effective. Okay, so here we go. This guy very clever. He came up with this theorem, or he discovered that for a closed-loop system like what I have here in the block diagram, the system for the closed loop will be stable if the open loop transfer function, G times K, will give you the frequency response, or will give you the frequency response using the polar plot or Nyquist plot. If that response encircles the -1 plus J0 point, exactly P0 times anticlockwise, where P naught is the number of open loop poles in the right half of the S-plane. So basically what that says is, say for example, if your open loop is unstable. Unstable is indicated by open loop poles on the right hand side of the S-plane. So if your open loop system is unstable and you have P0 number of unstable poles, okay, then the Nyquist plot or the polar plot of K times G must, in the S-plane, must goes around the -1. That's the negative, on the negative axis of the real, sorry, let me rephrase. That -1 is on the negative part of the real axis. If your Nyquist plot goes around that point exactly P0 times anticlockwise, it matters, direction also matters, then your closed loop system will become stable. Now, to interpret that, for most cases, if my open loop system is stable, i.e. I have no unstable poles, so P0 equals 0. In this case, what that says is that the closed loop system will also be stable if the polar diagram or Nyquist diagram does not encircle the -1 point in the S-plane. It encircles 0 times. Okay, so that's the criteria. I have a couple of examples here just to illustrate that point. Now here we are. I have a closed loop system where the blue line on the left top diagram shows the root locus. No, sorry, I keep saying root locus, but it's not. Shows the Nyquist plot of the open loop transfer function. Okay. Now open loop system is stable in this case. Now look at my axis. This is real axis. Okay, so this is imaginary axis. The -1 is here. Okay, this is the point where the Nyquist theorem says it's -1 plus J0, because the imaginary part is 0. It sits on the real axis, but value is -1. Okay, so I use a cross to represent that point. Now in this case, the Nyquist plot goes around like that. Okay, goes around like that. it doesn't cover this minus 1 point. Now that says, because my open loop is stable, so I got no positive poles, or I got a zero number of positive poles, then the Marquis plot should not encircle the minus 1 point for the system to be stable. In this case, it does not. Okay, it's actually it's on the other side of that minus 1 point, so it doesn't cover the minus 1 point. So the closed loop system should be stable as well. Now I can confirm that. Then I went on to run a computer simulation to show me the results. My input is a step, and my output, you see, is a sinusoidal kind of input response, but this sinusoidal gradually settles down. Now this sinusoidal is not due to the input, it's due to the complex pole, or the imaginary part of your pole. Okay, so this is in the transition period. And my input is a step, so I expect that to settle down. Okay, so but there's some wobbling here, but it is stable. That confirms, really, in this case, the Marquis stability criterion does apply. Now, if I change the controller a little bit, I get this result, the next one, sorry. Now this time, the Marquis plot, because now G remains the same, the plot is the same, but I change the controller a little bit. Now, if you look at the Marquis plot of G times K, okay, it needs to be both in there. Okay, Marquis plot of G doesn't cover everything. You need to have the Marquis plot of G times K. So both plot and controller needs to be included. This time it goes around like that in circles and then goes around there. Now you can see this cross is actually inside of my Marquis plot. Now my open loop system is stable, and I don't want the Marquis plot of K times G to encircle that minus 1 point, but it does. If it encircles it, then you have unstable system because of the stability criteria. So now I can confirm that. You can see the output is, again, you see a sine wave there due to the complex poles, but the amplitude of that sine wave goes up. Eventually it gets to infinite. Okay, that's no good. So that's confirmed. So the critical point here is this. It's this minus 1 on the real axis. Okay, so if it encircles it, then you have an unstable closed loop system. If it does not encircle it, then you have a stable system. That's all if your open loop plant is stable in the first place. Okay, it gets a little bit tricky when your open loop system is unstable. And not only we want system to be stable, we want system to give some margin for error as well. Okay, give some safeguard basically. We want it stable, but we don't want poles to sit on the imaginary axis. So that will give us the marginally stable system. We want more. We want system to be a little bit more. So this is what it is. If you're going to use the Marquis plot for your design, minus 1 plus J0 is there. Okay, it's that point there. Now, if your open loop system is stable, you don't want the Marquis plot of K times G to go outside of minus 1, so it needs to be somewhere inside. Okay. Now, the distance between that point and this is your margin. That's your gain margin. If you increase the gain by that much, then you have a problem. The measure of gain margin in this case is basically 1 over D. That's how much gain margin means, how much gain you can increase before it becomes unstable, or before the closed loop system becomes unstable. Okay, so that's how you measure the gain margin there. measure that distance, 1 over that, that's your gain margin. You can convert that into dBs, as we normally do, with 20 log 10 1 over d. There's also a phase margin as well, because Nyquist plots is formed from AC gains. AC gains have phase and magnitude. Okay? Phase margin is measured by this angle, where the Nyquist plot crosses the unit circle. Now this circle, the center of that circle is the point of origin. The radius is 1. The point where it crosses this circle, and if you draw a line from point of origin towards here, at this angle is how much phase, how much negative phase you can get before the system becomes unstable. That's called a phase margin. Okay? Now, typically, gain margin represents how much gain you can add as extra before system becomes unstable, or the closed-loop system becomes unstable. Phase margin is how much delay, the further delay you can get in a system before a system becomes unstable. Okay? Or delay, if you think about it, if you think about that in the context of a sine wave, delay means negative phase or negative initial phase angle. So this is the extra phase, negative phase angle you can afford to have in your frequency response before the closed loop system becomes unstable. Now that's when you use Nyquist plot. I can translate that for the bow plot as well. For a stable open loop system, if GS and KS do not give you any unstable poles or do not give you any positive poles, right? And you draw the bow plot of K times G, the closed loop system will be stable, providing that the gain plot, okay, of the open loop response, gain or the magnitude plot, gain magnitude is the same thing, okay, provide the magnitude plot or the gain plot of the open loop response, that's K times G, goes below 0 dB, that's crosses 0 dB, before the phase plot crosses minus 180 degrees. Now it's a slightly vague definition because it's hard to, perhaps it's a little bit hard to understand it. But I have a better way of interpreting this for stability. Now if you have a bow plot of K times G, you find the frequency at which the magnitude crosses 0 dB. So just go across, find 0 dB, and then find that particular frequency, omega c. Then you go to the phase angle, phase plot. Find the phase angle where for 180 degrees or minus 180 degrees. The minus sign is here, okay? It just got a bit muddled on this side. Find the phase angle at minus 180 degrees. And then find the corresponding frequency for that. So you have two frequencies here. One frequency is where the magnitude plot, on the magnitude plot, the magnitude of the gain crosses 0 dB. The second frequency, omega 2, is on the phase plot, the phase angle crosses minus 180 degrees. So I have two frequencies here. Now these two frequencies, if they are different, and if the first frequency from the magnitude plot is smaller than the second frequency, then the closed-loop system will be stable. But on the other hand, if omega c is greater than the second frequency, then the closed-loop system will be unstable. If they are the same, then you have a marginally stable system, and the closed poles will be sitting on the imagined axis. So that's the way to do it. I'm going to give you some examples here. Now I've shown you here in this diagram, the blue lines are the magnitude plot and the phase plot of an open loop transfer function. That's the open loop. That's G times K. So that's a Planck and K. Okay. The GS is the transfer function of the Planck. KS is the transfer function of the controller. So I have magnitude plot, I have the phase plot. Okay, magnitude plot goes down as the frequency goes up from a positive phase dB to negative dB. The phase angle goes down as well, starting from minus 90 degrees and gradually goes down quite a bit to minus something quite high, minus 540 degrees. Now the real axis, now this time we need to be careful when we read values out of the plot. Real axis is in the log scale. So for example, this is 10. The next division would be, sorry, this is 10 to the power of 0. This is 1, therefore. This is 10 to the power of 1. So this is 1, this will be 10. Now this graph is produced by MATLAB. MATLAB does some automatic scaling for you. It actually draws some grid in between. So if that's 1, that's 10. The grid in there, if that's 1, the next grid, that's grid here, will be 2. Next one will be 3. Next one will be 4. Until you get to the ones here, this will be 9. This now comes down to 10. A lot of people make this mistake. They see a 1 here, so they see this. Therefore, they see 1 here, and they would assume that's as a 2. But it's not. This is 1. The between there, you actually moved from this division to that division. Between there, we have 9 different values here, but that's all marked by the grid as indicated. They are not linearly distributed. Okay, because we use log scales. So read that. Based on that, now we can read the values. The first thing I want to do is to find omega c. Omega c is where the magnitude goes across 0 dB. So you need to identify where 0 dB is. Draw a dotted line across until you see it intersects with the blue line. Blue line is my magnitude plot. Okay, and then you draw a vertical line to identify the frequency. So over here, this is my red line here. So this is 1, this will be 2, this will be 3, this will be 4. Next one will be 5. So this will be 4 point something. Let's say I estimate as 4.3. Okay, so my omega c equals 4.3. That's my first frequency. Then I need to identify the second frequency. Second frequency is from the phase angle or phase plot. Across is minus 180 degrees. So on the phase plot, find where the minus 180 is. Draw a line, a dotted line across until you see it intersects with the blue line or with your phase plot. Okay, and then you draw a vertical line and you can identify the frequency. This time, this is indicated by the green line here. So it's 1, 2, 3, 4, 5, a little bit over 5, say it's 5.1. Okay. Now, omega c in this case is 4.3. omega 2 is 5.1, omega 2 is less than omega 2. Therefore, the closed loop system will be stable. Okay, that's how you apply the stability criteria to a bow plot. Now remember, this plot is actually an open loop plot. We are trying to make a judgment on the stability of the closed loop system from open loop frequency response plot. Now change the open loop frequency response a little bit. That is a different system. What I have here is for the McLeod plot, again, I'm going to look for the omega c. So I'm going to draw a line from 0 dB all the way up until it intersects with the blue line, the McLeod plot. And then I'm going to draw a vertical line there, and I'm going to read that value as my omega c. So 1, 2, 3, 4, 5, almost goes to 6. So let's say it's 5.4. And I need to find omega 2. Omega 2 comes from the phase plot. So I need to go to the minus 180 degrees, draw a line across until it intersects with the plot. And then at that point, you draw a vertical line and you can read the frequency. That's 1, 2, 3, 4, 5, just exactly on the 5. This time, omega c is greater than omega 2. So the closed loop system will be unstable. Now, between these two examples, one is stable, one is unstable. Okay, the GS, the plant, is the same. The only thing I have changed here is actually I increase the control gain a little bit. Okay. First case, the control gain was smaller, so the system is stable. And if I increase the gain a little bit, then the system becomes unstable. Okay. I've got a couple of, there's another example here. In this case, I'm not too worried about stability. I explain why. I have a bow plot of G times S. That time is entirely a different system. Okay, so assume I know G and I have K. This is the bow plot. Now, first of all, I'm going to find omega c. So omega c is coming from the McLeod plot or the gain plot. So I've got to find 0 dB for my gain. I'll go across until it intersects with the blue line, and then go down, find my frequency omega c. Now this time, this is 1, this is 2, this is 3, just slightly over 3, maybe 3.1, 3.2, so I just say 3.2. That's my omega c. And then I need to find omega 2. Omega 2 is the point where the phase plot drops below minus 180 degrees. So I go to the phase plot, I find 180, and I'm going to draw a line there. I can see this blue line. In fact, this blue line does not actually ever drop below 180 degrees. It's a typical characteristic of a first or second order system. First order system, the change of phase angle is maximum change of 90 degrees. Second order is 180 degrees. So first and second order systems, unless they are unstable in the first place, normal stable first and second order system, they do not go across minus 180 degrees on their phase plot. So because they never goes across minus 180, therefore the omega 2 is actually, you can consider omega 2 as infinite. Now if it's infinite, then of course omega c will be less than omega 2. And of course the closed loop system will always be stable. So that's kind of stuff that you need to consider when you think about simpler or lower order systems. Okay. Now it's your turn. I got a couple of block diagrams here. This time, now let me just show you a little bit more, expand a little bit before you go away and do it. This diagram is a bulk plot, the magnitude and phase of the plant GS. And it does not include Ks in there. But what I said here is say, assume Ks equals to 1. Then, of course, K times G equals to 1 times G. And therefore, it's the same as G. Therefore, this diagram would be the bulk plot of G times K. I'm just trying to raise the awareness. K makes a difference here. Okay, so you end up with this diagram representing the frequency response of K times G because K equals to 1. And I'd like you to determine if the closed loop system will be stable or not, just using the approach that I did earlier. Okay, for the second question, now again, I'm giving you the frequency response of the open loop plant. That's a frequency response of GS. It does not include K. I'd like you to determine if the closed loop system will be stable or not. In two cases, in one K equals to 1, in which case this is the same as K times G. But second part is when Ks equals to 10. So your K times G, if I want to know K times G, you need to think about what to do with this Q, because I have a constant. Another word, you have to add 20 log 10 to the magnitude plot before you determine if the closed loop system is stable or not, or before you find the two frequencies. Okay, because if you change, if you add 20 log 10 for the second part of that question to the magnitude plot, this whole thing goes up. Therefore, the frequency where it crosses 0 dB will be different from this plot. Okay, so you need to be a little bit careful with the second question. Okay, so that's what I'd like you to do. Okay, thank you.